All right, thanks for tuning in, everybody. This will be our last notes day for Honors Chem this year. I recommend checking this out if you did miss Tuesday because of either AP testing or you were just absent or whatever. This is the end, strong versus weak acids. I'm going to run through what we did on Tuesday. 4 terms we're going to bring up today are vocab terms, or they were vocab terms, most from about a month ago, but one of them was from a couple weeks ago. So strong and weak acids. Strong acids dissociate completely. Dissociate means that they break up. Okay. So an example of a strong acid that we've used this year has been HCl. When HCl dissociates, it breaks up into H plus and Cl minus. The thing is, it dissociates completely. What that means is that it all breaks up into those 2 ions. So if we're doing a KEQ value for this, what we're going to do is use what's called a Ka value. A stands for acid. It's the same as a KEQ. Don't worry about it. Again, K values are products, so products over reactants. If you think about the Ka of this, if it breaks up all into products, you're going to have a huge numerator and an itty bitty denominator. So the Ka's of strong acids are big. How big? Too big. So we're not going to worry about the strong acids too much. But on the other hand, if you look at weak acids dissociate minimally. What that means is that they pretty much stay intact, but a little bit breaks off, just a little bit. A very popular, not popular, but it's popular in a TV show, Breaking Bad, hydrofluoric acid, HF, is a popular, well, at least again in the show, is a weak acid. What that means is that it minimally breaks up. So it dissociates a little bit. Note, we're in equilibrium, we have those little arrows. So since only a little bit breaks up, the K value for this would be the opposite of the strong acid. The strong acid was gigantic. The Ka of weaks are going to be tiny because it's just basically flipped around. We have minimal products and a lot of reactants. So any fraction where your numerator is tiny and your denominator is big, you're going to have a tiny number. So the math of weak acids, we're going to do one example up here. And again, you can pause it to actually read what's going on here. We have an unknown weak acid. HA is my made-up formula. So what I'm going to do is break up HA into AH plus and A minus. On my left side, I'm going to write my quick, Ka expression, which would be H plus times A minus over HA. I need to find the H plus. Eventually you can get the pH, and later I'll show you how, but you just negative log the H plus. We got to find the H plus concentration, so we need this guy at equilibrium. So we don't know anything at equilibrium here. So I'm going to make an ice table with my weak acid. I'm given my initial molarity of HA, which is going to go right down there. So my weak acid, HA, it doesn't matter what it is, it's just HA. H is the hydrogen, A is the anion. It could also be A for weak acid. So 1.5 molar is HA. I'm not given any information about those. You can assume those are 0. Since those are 0, check out again the other video about the ice tables. You could assume that the change goes right because you got to make some products. You can't take away from 0 and get negative products. So again, equilibrium is just whatever the initial is added onto the change. All right, so we have x there, 1.5 minus x there. What I want to do now is take a minute and plug all these numbers, including my Ka value up here, into my expression. So I'm going to do that underneath here. What was it again? 3.4 times 10 to the negative 6th equals, I've got x squared over 1.5 minus x. All right, so this is the critical part of the weak acid equilibrium. If you like the quadratic formula, you can use it because you have an x squared, you have an x, and then you could figure out what's going on when you multiply those and distribute and whatever. But we can make a critical assumption that'll help us out in the long run. Ka for weak acids, the K value is so small that the change, in other words, the x value, is going to be really small. Like, it's close to 0. X is pretty much close to 0. It's kind of like weighing yourself with your shoes on, but then weighing yourself when you take off one shoelace. It's like you're still pretty much the same weight. It's just you're maybe a slightly lighter, but it's pretty much the same thing. If you take anything, any number, like in this case 1.5, and subtract it from a number close to 0, what happens is the x pretty much means nothing. In this case, the minus x. This makes your math much easier. Again, this is only because your K value is super small. On all other equilibrium problems with your K value not super small, like times 10 to the negative 6th, like it is here, you have to do the regular ICE table math and do the square roots and all that. But for this, it makes it much easier. So if I multiply, I'm just going to quickly finish this one off. If you multiply those together, you would get 5.1 times 10 to the negative 6th equals x squared. And again, once you solve for x, I would square root both sides. You will get x to be about 0.0023, which, if I scroll up here, which is your H plus concentration. All right? Again, pause it if you need to take that in for a minute or so. And again, negative log of H plus equals your pH. So if you negative log that, you should get a pH of around 2.64, which shows, again, it is an acid. So it's a lot of work here. Over time, you might learn that there is a shortcut to this. You actually don't even have to do the ICE table. It's just doing the ICE table helps organize your thoughts, and it helps prove that the equation works. So that is it for weak acids. I do recommend, again, checking this out. There is an assignment on haiku. Thanks, guys.